So today we are going to look at differentiation, and as our objectives of the day, we are going to look at the general rule, okay, for differentiation. We're going to look at the product rule, the quotient rule, the chain rule, relationship between dy dx, dx dy. We'll be looking at how to differentiate special functions like exponential function, the logarithmic function, or the lane function. Then we also look at a trigonometric function, okay, and how to also differentiate the inverse of three functions, hyperbolic functions, and so on and so forth. Okay, and between now and the next two lectures, that is from lecture 8 to lecture 10, will be on differentiation. And to wrap up on the aspect of differentiation, we'll be looking at applications of differentiation. Okay, good. But today our main focus will be on the very first, let me say 3 or 4. Okay, that will be our focus for today's class. Good. Now let's begin. Yeah, so the first thing we are looking at is the general rule on differentiation. Okay, good. And as we are moving on, I will get to the points on applications, and I'll touch on the relationship between the limits and differentiation itself. So I've skipped that aspect, okay, of differentiation from the very first principles. Today, we want to move straight to the rules. We want to know how to differentiate, okay? Then eventually we'll return to look at a connection, okay, between the limit of the slope and the derivative. Good. General principle of differentiation. Now, if we're given any function, okay, y is equal to x raised to the power n. Okay, then the rule says that when you differentiate, it's going to be what? Bring the power to come and multiply, and then subtract 1 from the power. Okay, so the derivative is going to be equal to n x raised to the power n minus 1. Okay, and sometimes you write the derivative using various notations. Okay, one notation is to write it as dy dx. Another notation is to write it as what? Y prime. Okay, and sometimes we use d of x. Okay, they are all the derivative of y with respect to x. Okay, very well. So we are saying that if we are given the function y equals to x raised to the power n, then the derivative will simply be bring the power down, okay, to multiply the x and then subtract 1 from it. So let's take a typical example, okay? If we have something like x raised to the power 3, then the rule says that dy dx, okay, dy dx will be equal to what? It says bring the power down, okay, to multiply the x. So that would be 3x, okay, raised to the power 3 minus 1, okay, and that will give us what? 3x raised to the power 2, okay. That is the first principle of the differentiation, okay. Good. Let's take another example. Let's say we have y is equal to 2 raised to the power x, sorry, 2x raised to the power, say 5. If we are to differentiate it, then dy, okay, dy dx will be equal to what? 2 times 5, okay, x raised to the power 5 minus minus 1, okay, per the rule. So this will give us, this will be equal to what? 10x raised to the power what? 4, okay, good. So basically, this is what the rule of differentiation tells us, okay, good. Now, there can be, let me say, a combination of terms, okay? So for example, you can have functions like y is equal to x cubed, okay, plus 2x raised to the power 5, okay? The same principle applies. When we are differentiating, okay, you differentiate them individually. Good. So you differentiate the s cubed just like you have, and then come and differentiate the 2x raised to the power 5 also separately. And the final answer is going to be what? When we differentiate s cubed, we get 3x raised to the power 2, okay? Plus when we differentiate 2x raised to the power 5, we got 10. Let me just separate these two sections. So we get 10x raised to the power 4. Okay, good. So which brings us to the next principle. Okay, but before we look at that, let me find out if there are any questions for me. So the next example will be y equal to, let's say 3x raised to the power 4, okay, plus 2x square, okay, good. Let me just add this, plus let's say x, okay, and let's differentiate as c. So which means that our derivative, this time using the second notation, which is y prime, is going to be, the rule says we should bring the power down, right, to multiply. So that would be 4, okay, times 4 times 3x raised to the power 4. Then you subtract 1 from the power, okay, plus we bring the power to come and multiply. So that will be 2 times 2x raised to the power 2. Then we subtract 1 from it, okay, then plus, this time the power here is x raised to the power 1, right? So when we bring it to multiply, that will be 1, okay, times what? X raised to the power 1 minus 1, okay? So when we simplify this should give us 12x raised to the power 3 plus 4x raised to the power 1, okay? Then plus 1 times x raised to the power 0, okay? But we all know that any number raised to the power 0 is 1, right? Good. So which means that we can just write at this side, this is 1 times 1, which is 1, okay? So the final answer is what? Is 12x cubed plus 4x plus 1, okay? Good. So that's the derivative of the given function. Good. So basically that is the rule. Try this for me at home. Try it at your end. So let's have 5 over 4 x raised to the power 4 plus, or let me say minus 3x raised to the power 2, okay, plus 2x. So try that for me and give me the answer. Okay, you raise your hand and give me the answer. Okay, so let me have your answer. I think Alex. Yes, Alex. Alex Salasi. You can unmute yourself.
Hello, sir.
Yes, Alex.
Yeah, the answer is 5 minus 6x plus 2.
So 5
S cubed.
S cubed minus 6x times 2, which is very correct. Okay, so that will be our answer to this particular question. Thank you, Alex.
That be 20.
Yeah. So let's continue. I think by now everybody is okay with the first principle. So let me proceed. Okay. So that's the general principle. And then that is the next principle we just made use of. So we are saying that if the terms are added, okay, just like we had something like 2x cubed plus, or if either plus or minus, maybe 3x raised to the power 2. Okay, how do you differentiate? This one is saying the derivative is just differentiate this one plus differentiate this one, and you get the final answer. I think we have already looked at that in the previous example. Now, the next thing I want you to note before we move on, okay, is that anytime we differentiate a constant, okay, so for example, oh, sorry. Okay. So for example, if we differentiate a function like y equals to 2x cube, okay, minus 2. 2 is a constant, okay? It's a constant because there is no variable attached to it. So that makes it a constant. So anytime you differentiate a constant, you get 0, okay? Good. Now, and someone will ask, why is it so? Okay, it's because there is a 1 here, and that 1 just represents x raised to the power 0. So when we are differentiating, okay, this per the rule, y prime is going to be, sorry, y prime will be 3 times 2 x raised to the power 2, okay, minus, you see this 0 will come down, and that will be 0 times 2, okay. So that makes the whole thing equal to 0. So anytime you differentiate a number without an alphabet, which we refer to as a constant, you always end up getting what? 0, okay. So you need to take note of that particular, okay, principle too. Good. Now moving on. The next principle we are looking at is the product rule. And the product rule is quite simple to use, okay? What it says is if you are given the product of two functions, say u and phi, okay, then all you need to do is to apply this principle. So an example of u and phi will be this function we are seeing down here, which is x raised to the power 4 times 3x plus 2, okay? Another example is if I have, let's say 3x times maybe 4 x raised to the power 2. Okay, this is also of this form. It's also of the form u v. Okay, another example too could be having let's say x times sine of x. Okay, they are two different functions. Okay, multiplying each other. Okay, good. And we are saying that anytime we have the product of functions, we make use of the product rule. Okay, so this is the rule which we're going to apply. It says that to differentiate y, okay, make one of the functions u, make the other v, and then apply the principle that dy dx is going to be u divin dx plus v du dx. Okay, good. So a typical example will be what we have over there. We have to differentiate this function, okay, to find dy dx if y is x raised to the power 4 times 3x plus 2. Okay, and we are saying that we want one to be u and the other to be v. So we let u to be equal to x raised to the power 4 here, and we let v be equal to, okay, so this is it. We'll let u be equal to x raised to 4 and v be equal to 3x plus 2. Okay, then what next? The rule says that we first have to find divin dx. Okay, this is it. We have to find divin dx. So we'll differentiate v with respect to x and also differentiate u with respect to what? X. Okay, so we are going to do that. When we differentiate v with respect to x, okay, this will give us 3. So when we differentiate 3x plus 2, when we differentiate 3x, we'll get 3. When we differentiate 2, you get 0. Okay. And when we differentiate the u with respect to x also, okay, the u with respect to x is going to be 4x, okay, 4x raised to the power 3. Good. So that is the u dx as well. Then to find our dy dx using this principle, we'll just substitute the values we have here in there. So our u is what? X raised to the power 4 times divin dx, okay, from here. So our divin dx is what? 3. So times 3 plus the next thing is v. So v is what? V is 3x plus 2. Okay. Then the u dx, this is the u dx here, which is what? 4x cubed. Okay. And this simplifies into 3x raised to the power 4. Okay. Plus, of course, 3 at this juncture, we will just keep it as this, or we can expand and simplify. Okay, good. So 3x plus 2 times what? 4x cubed. Okay, very well. So like I said, we can still expand and simplify where necessary. Good. So basically, this is what the principle talks about. Now let's try another example. Okay, good. In relation to the same formula. Okay. Yeah, so we'll keep this question, we'll answer it later. But for now, let's try a much simpler example. Okay, so using a polynomial function. So we have y is equal to, let's say, 3x raised to the power 4, okay, times, let's try 5x raised to the power minus 3. Okay, good. So let's give it a try and see how it goes. So we are saying that in all cases, we will let, okay, since we are applying the product rule, we'll let one of the functions be u and the other be equal to phi. So in this case, our u will be what? U will be 3x raised to the power 4. And phi is going to be what? And phi will be 5x raised to the power minus 3. Okay. Then what next? We'll have to find the u dx. So we'll differentiate u with respect to x. And that should give us what? That gives us 12x raised to the power 3. Okay, and then we also differentiate phi with respect to x. And that will give us, when this comes, to be -3, right? So we get minus 15, okay, x raised to the power -4, okay? Then what's next? The rule says that dy dx, okay, will be giving us u divin dx, u divin dx, okay, plus phi du dx. That is the principle, okay? So this will be equal to, now your u, we know u is what? 3x raised to the power x raised to the power 4, okay? So this is u, 3x raised to the power 4. So we put it in the 3x raised to the power 4, okay? And then this is divin dx, okay? So divin dx will be minus 15 x raised to the power minus 4, okay, plus, now the next thing is phi, okay? This is our phi. Phi is 5x raised to the power minus 3, okay? Then the final thing to bring will be du dx, which is 12x raised to the power 3, okay? Good. So when we simplify this, this will give us what? 3 times 15, which is minus 45. So we have 45 x raised to the power 4, okay, times x raised to the power -4, okay? Per the rules of indices, this will be, you take just one base and add the exponents, okay? Good. So that gives us s raised to the power, okay, 4 minus 4, which will be 0. Okay, let me just write that for the meantime. So x minus 4, then this is 5 times 12, which gives us 60. Okay, and then once again we have x raised to the power negative 3, okay, times what? Sorry, plus 3 here, okay. So this is going to give us what? This is going to give us minus 45, okay, plus 60, which will be equal to what? Which will be equal to 15, okay, good. Now, if we're comparing this principle with, let's say if we are trying to multiply, okay, these two functions before we apply the rules of differentiation, it would have looked like this. Y is equal to 3 times 5 is 15, okay? Then x raised to the power 4 times x raised to the power minus 3 will be x, Okay, the powers will be 4 minus 3. So that will be x raised to the power 1. And if we were to find y prime, it will be equal to 15. Okay, x raised to the power 0. X raised to the power 0 is 1. So the final answer will be 15. Okay, good. So this is how to look at, right? And we can clearly see that we had the same answers. Okay, but the question is not about this being simple. Okay, we are saying that in some cases you can't multiply the functions. So in such a case or such a scenario, you have no choice than to make use of the product rule. Okay, good. So that is what we are demonstrating here. So in the, if you look, for example, you have x squared times e raised to the power 2x. You can't multiply to simplify before you apply the general rules, right? You still have to count on the product rule. So here we are trying to demonstrate how to use the product rule, not concentrating on this simplification and then apply general principle of differentiation. So take note of that. Good. That's I think basically that is for the product rule. If there is any question, you can let us have it. If there is any question, you can raise your hand.